So if you recall, there's two categories of formulas: our definitions and our relationships. Our definitions are delta x is x minus x naught, which is displacement. We have the average velocity, which is the rate of change in displacement. And we have acceleration, which is the rate of change in velocity. And we have our average speed is total distance divided by total time. And we have our relationships, which are two formulas. And it's extremely important that we remember that this one and this one require, oh, I'm gonna give you the other one, which I taught you, you don't really need to ever use. This one, but we don't ever really need to use it. Those require acceleration to be constant. For those highlighted in blue, see that there. So what I've highlighted in blue is these three formulas require the acceleration to be constant to use them, and also this one here. So really, almost every problem you can solve using these questions. And I will tell you right off the bat, here's the secret trick to everything. If you get confused about how to solve kinematics problems, number one is try average velocity. That means try this and then try this. I call this average velocity 1 and average velocity 2. And if that doesn't work, use something called the average velocity table, which I will teach you here today. And the third thing to try is v equals at plus v0. And the fourth thing to try is x equals 1/2 at squared plus v naught t plus x0. If you can't solve the problem using those four, then you've done something wrong, because that's everything. So what we have here, so our approach to analyzing graphs is always OY, ZER, SA. Origin, y-axis, and the error bars, x-axis and error bars. What we can read, which are the axes, slope dividing the axes, and area multiplying the axes. So we see we've got 0, 0 there with positive values here and positive values here. So that means that on the Cartesian plane, we're actually looking at a graph that's right there. All right, so there is a 0, 0, but it's quadrant 4. Next thing, the y-axis is y measured in meters, and the x-axis is x measured in meters. Neither has an error bar associated with it. So this is actually a picture of space. So if this were taken in the dark and this projectile had a flashing light that went off every 0.5 seconds, and we made a movie, this is what we would see. This is an actual picture. It's unlike the other time variant graphs that we have. All right. So what we know then is that if we were to write coordinates, we had time and x and y. At time 0, we have an x0 and a y0. At time 0.5, we have an x of 5 and a y of -2. And at 1.0, we have an x of 10 and a y of, what is that, 4.5 minus 4.5. And at time 3, we have 1.5, an x of 15, and a y of -10. And at 2.0, we have an x of 20 and a y of -16. And 2.5, our last, is 25 and -25. So we want to know, what was the initial velocity which the projectile was launched? Well, what we know is that every instant in time, if we were to connect these as a smooth curve, like so, we of course get a downward cupping parabola. And at any moment in time, there is a velocity vector that is tangent to that curve. So our velocity vector at, say, point E looks like this. It's in that direction, it's tangent. And it has a horizontal component and a vertical component. Just as here, there is a horizontal component and a vertical component. And here, there is a horizontal component and a vertical component. So whenever we have two-dimensional motion, we have to treat each dimension separately. So a way to think about that is, if we have our x dimension, our horizontal dimension, we could write an equation that describes its velocity and also one that describes its position. And we could do the same thing for y. We can have an equation that describes the velocity in the y direction and the position in the y direction. So if we were to put in the values for these, the velocity at any given time is equal to the acceleration in the x direction. Well, let's see, what is the acceleration in the x direction? If I do a projection of these points up here, the x coordinates, that is the number line. The number line is the projection. So if we went from 0 to 30 in the x direction, that would be, this is the first dot, this is the next dot, the next dot, the next dot, the next dot, the next dot. What's the value of the acceleration? Well, let's check this out. Acceleration, the definition is delta v over delta t. So let's find out the average velocity during this time interval. It went 5 meters in 0.5 seconds, so it has a velocity of 10 meters per second. Let's check the next time interval. It went 5 meters in 0.5 seconds, so its velocity is 10 meters per second. 10 meters per second. Wait a minute. What's the value of the acceleration in the x direction? Delta v, let's see, 10 minus 10 over 0.5 is 0 over 0.5 is 0. The acceleration is 0. There's no acceleration in the horizontal direction. This is one thing we know about horizontal projectiles. We should just know it as a matter of course. There's no acceleration in the horizontal direction because there are no forces acting on it. F equals ma. F in the x direction is directly proportional to the acceleration in the x direction. If the acceleration in the x direction is 0, doesn't matter what the mass is, the net force is 0. So when this projectile leaves, if we draw a free body diagram on it, this is the only force we have, the weight. After it's released, that's the only force acting on it. So that's the only acceleration. So x has no acceleration whatsoever. All right, so we have an acceleration of 0, and the initial velocity, well, is 10 meters per second in the x direction. So our velocity is 10 meters per second. If this thing is launched horizontally, like say if it were a ball that rolled off or it was fired off, what would the velocity vertically be the instant it leaves contact with that ledge? It would be 0. It's free fall. How do we know this? Well, just as this is the x direction number line, we could have a y direction number line, and those points from 0 to minus 30, with the points in red, the projection we can see the distances are getting larger. So if in equal time intervals, those are equal time intervals, it's traveling greater distance, that means the velocity is changing, it's increasing. But you can also see that the velocity is 0 in the beginning. Launched horizontally, horizontally means its vertical velocity is 0. So velocity here, in this case, acceleration is some number minus g, we don't know what it is, times t, and the initial velocity is 0. So the velocity in the x direction is 10. The velocity in the y direction is 0. The question we're being asked is, what is the initial velocity with which it's launched? Well, initially, there is a horizontal velocity vector of 10 meters per second, and the vertical is 0. So therefore, the initial velocity is 10 meters per second. Now, that's different when we get down here because we still have this 10 meters per second, plus there's now a vertical velocity, which would give an overall velocity. but that vertical component at the top is 0. How's that? Is there anything that I drew there or explained that seems new or foreign to you?
No, I just didn't analyze the graph visually enough.
Devil's in the details, and that's one thing that they're always sorting out with physicists, looking for those details. Have a thought, Leo? What did you give as an explanation?
I said you can tell because the projectile moves uniformly, meaning there is no air resistance.
Okay, so it has no air resistance.
Well, no significant air resistance.
Because it's using uniformly because there's no air resistance.
Mm-hmm.
Yeah, you sound skeptical. So this is the challenge, and this is good that we're coming across this, because this is about writing an answer, a solution for the AP. They want there's a particular format they want to explain things. And it goes like this. The general format of it is fact, observation, and then connecting logic to the conclusion. So if there was no significant air resistance, then what would be true? Anyone can answer this. If there's no significant air resistance, what would be true?
There's constant velocity.
Does it have constant velocity, something that free falls?
Oh. Wait, that would be constant acceleration for something that free falls?
All right, so what I think I'm going to do here is and I want you to tell me when I'm done if you feel it was not a good use of time. But I want to give you some real concrete strategies for dealing with two-dimensional motion. So the first thing is that each dimension must be treated separately. Each dimension must be treated separately, X, Z, or Y. Each one must be treated separately. 2, accelerations are caused by forces. And that relationship is Newton's second law, F net equals ma. And to illustrate a couple of these concepts, I'm going to show you a couple things quickly. So you see that device is designed to release that ball, drop the other side so we can fire it horizontally. The one mechanism does both. So when he pulls the lever, they're both going to be released at the exact time. Listen. And listen again. What's the conclusion?
They land at the same time.
Right. Horizontal projectiles take the same time to hit the ground as one that is dropped. In other words, horizontal velocity has no effect on free fall time. That's staggering. Almost everyone would think that it would take longer for the horizontally fired ball to hit the ground. What we know is then that there's a simple reason to explain that. And that is, if this ball is dropped, it is going to be accelerated and have a motion dot diagram like that, because the force acting on it is gravity. And when we fire one horizontally that has an initial velocity, it is still going to be fall the same amount because it is accelerated the same amount by gravity. So that means they'll hit the ground at the same time. Now they won't have the same velocity because this will have the velocity, that vertical velocity. This will have that same vertical velocity v, but it will also have a horizontal velocity v, giving it a larger resulting velocity. So this one will have a greater impact velocity because there is a horizontal and a vertical, whereas this first one only has a vertical velocity. All right, so that's the first thing. The horizontal has no effect on free fall time. The second thing is that the force of gravity, or the acceleration caused by gravity, is 10 meters per second squared, or 9.80665 meters per second squared. You can use any number of significant digits you want. The AP is fine with you using 10. It turns out it doesn't make that much of a difference in your final answers. But we know it very precisely. But it's that level and it's constant. Whether you are at the surface of the Earth or you are on the top of Mount Everest, we're talking the same value of acceleration. It doesn't matter where you are. This is 10, 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 this is 10. All right, so that's the first thing to know about this is horizontal has no effect. The second thing is that for all normal locations without a significant change in R, G will be the same. Now, of course, by R, I'm referring to this R, these two R's, which are the distance between the centers. So if this is the Earth, top of Mount Everest won't even show up as a bump. So the difference, this R, from the surface of the Earth to the highest airplane that flies on the planet is less than the thickness of my pen here. So again, if this is the surface of the Earth and this is, you know, like this is like maybe the ISS, that's how close it is. Okay, so no, the G is the same when you're flying at 37,000 feet or 10,000 meters, 10,500 meters in an airliner or however. That distance, this R changes so little, the G remains constant. So that's the significant piece for this question, because if there were air resistance would affect that acceleration.